to introduce Maxime for the second talk of his series, which I guess is Conjectures on Stability Conditions to Stability in the Non-Archimedean Set.
Okay, thank you very much. Okay, so let's first just look for what is stability on a category. I have a translated category C, and I have a central charge additive map, complex numbers, and I get a bunch of full subcategory specific of semi-stable object with slope theta, and if you get an object with a central charge belongs to exponent of I theta, strictly positive numbers, so it's non-zero number, we see it in R, and for any object, finally, for any object on E, there exists a priori many of a posteriori unique hard-crossing integration. It means that you get just sequence of some object and inclusion interpret as some maps in translated category, finite lengths, and such things, and such a group sigma I are semi-stable. Okay. Now, so that's basic thing, and then there is also things like support property, which I will interpret.
You want to say that something is decreasing, or you assume that everybody knows
What?
Probably you want to say that theta is decreasing or something.
Theta is decreasing, yeah. It's strictly decreasing. And support property says that the values of central charge of semi-stable objects is a discrete subset. So this complex numbers. Yeah, so what are basic example? The most basic example is representation of quiver. Yeah. Get a quiver, Q, arrows, oops, and so on. You get path algebra of quiver, maybe also some field, and you can mod out by some relations, make some DJ quiver, let's do quivers with relations. And then consider categories of representations of quiver which are perfect as A modules, so finitely many pieces and finitely many dimension topology. It has a T structure, representations in degree 0, and so the T structure which correspond to the central charge is given by just bunch of numbers in upper half plane. Central charge is, you get some kind of numbers ZV in upper half plane, numbers. And for any representation, E will be some of vertices of the quiver, dimension EV or heuristic multiplied by ZV. And then I can automatically have harmonic filtration on heart of the structure. So what is filtration? Imagine that your field is now, let's say, complex numbers. And you get just, forget about vertices, you just one vector space. What is a filtration in vector space? Labeled by real numbers with finite many steps. So the kind of basic idea that real filtration, let's say on say complex vector space, finite-dimensional complex vector space over C, is the same as some equivalence class of families of norms. Paths in the space of norms. And of certain type in up to certain equivalences. So you have like norm depending on parameter some time. When time goes to plus infinity. And you say that you get kind of different pieces of iteration, sigma n, sigma n minus 1, sigma 1. Like these are real numbers now from 0 to pi for harmonic integration. And on kind of nth graded component, ith graded component, the norm grows when time goes to infinity. It's exponent minus t times theta I. And up to 1.
Максимальный норм заменит квадратик форму.
Hermitian form. Hermitian form. Hermitian form. Yeah, so you get like ellipsoid, which is very stretched. It's kind of very. So you get subspace when the norm is very big. So ellipsoid norm 1 will be very long in this direction. This gives you subspace. Then you get next subspace, and when you consider, like for standard unit ball in some coordinates, how these things will grow, and consider logarithm of norm divided by time, and get this gets a filtration. Yeah, so such.
I think I didn't understand at all this thing. Can you give one example of this?
Yeah, just consider diagonal family of things. You get minus d sigma n. Consider such family of Hermitian norms given by these matrices.
And what if your norm is not?
Yeah, no, it could be bad limit. It could be good. It could be bad families of norms, but you can consider families of norms that for any vector, non-zero vector. If, what is the property? Is that for any non-zero vector, if you consider the limit log of norm with respect to ht divided by t exists. Yeah, so that's the main problem. And this limit gives you which term of iteration your things stays in.
So I have a question about the definition of a stability condition. You said something about like the upper half plane. Is there in general for general stability conditions?
Sorry?
For a general stability condition, do you require something about like the upper half plane or?
No. It's the most basic example.
Yeah.
For stability condition, you have two things because you can shift by one. The center charge goes to minus.
What does it mean for theta to be ordered if they're like on the circle? Of
It's real numbers.
Oh,
You choose kind of on which part of shift of Hartree structure you do. It's like you choose argument of restriction of form to Lagrange. Yeah. So such things actually appears in dynamics, in kind of Lyapunov exponents when you get some dynamical stuff and then grows by Merkel-Kirchner-Gordic theorem, whatever. This you get automatically such filtrations in dynamical systems. Yeah. So the R filtration is kind of asymptotic behavior of some nice family of norms. That's the point. And for example, for this quiver, how we can characterize this hardware filtration geometrically? Yeah, you can consider quivers over C. And there is, first of all, this semi-stable objects. I consider just representation degree 0. Semi-stable objects are extension of something called polystable objects. And polystable objects by geometric invariant theory of slope theta, equivalent by JT kind of theory moment map to the condition that certain self-adjoint operator, which is sum over ZV projection to EV, it's operator on direct sum over all vertices of my representation of quiver, plus sum over you do the following. In my quiver I get some arrows, I denote by alpha, all correction of arrows, and I take operator of alpha, alpha star alpha. And the condition that this guy has argument 0. What does it mean? It's not self-adjoint operator, but this thing acts on my vertices, so that imaginary part commute with real part, so one can still have kind of orthogonal eigenvectors, and one can take arguments, you get complex numbers, and this all complex numbers should be theta. So we get this condition, it's exactly condition of stability. So it's on such thing, my flow of norms should have speed exactly theta.
Sorry, that should be equal to
Theta,
theta.
to theta, yeah. On such norms, the flow should be kind of rescaling according to this picture. So h should be equal to exponent minus theta t times some h0. And there is this gives the following suggestion. Let's consider the following flow on Hermitian norms. Dot will be derivative with respect to time. It will be minus argument. It's a self-adjoint operator. So the derivative will be of norm will be self-adjoint operator of this 6. And the claim that this flow in a very large time kind of will give you Cardinal infiltration naturally. So it will be on different pieces.
This is a flow on what?
On the space of Hermitian, collection of Hermitian norms on my representation of queer teach it's just still speak about queer representation. Yeah, so you get this picture. So the filtration appears at the limit when you study growth of these norms.
It's like those
Sorry?
It's like those right?
No,
Why?
it's not. Not exact. No, it's there are different flows. It's not. No, it's really new flow. It's really it was with Mill and Branagh and Fabian.
Just to understand. So on one side is a number argument.
On the right side, yes. So the argument is a number.
Times identity operator.
Ah,
Sorry. And here it will be. It's operator, yeah.
And the argument in terms of some Kerr decomposition.
It's what's called normal operator. It's imaginary part commuted with real part. So it has kind of common spectrum, which is orthogonal, a bunch of complex numbers in upper half plane, and you can see the argument of this.
All arguments are the same now.
Yeah, and you get operator replace eigenvalues by arguments.
so this argument is some diagonal matrix now, not scalar?
No, it's some matrix. It's a matrix which is diagonal in some orthogonal basis.
I see. It is a sum matrix.
Yeah.
Can you say exactly what argument means?
Yeah, you have operator.
Coordinates of matrices.
You know what it's.
What is it?
You have operator, and this operator you can write
Unitary.
times unitary exponent I argument times m. M will be square root of m cross half, and this will be self-adjoint operator as well. No. Now, so get this flow, and I think we proved that this converges it gives a large time behavior will give you Cardinal infiltration. But in fact, in our complex numbers will be some more complicated picture, because here you can see the coefficients of logarithm of norm divided by t and make limit. But then the symmetric expansion get log t, log t, and then we have this complicated paper about iterated logs which appear in this story. And today this thing will not appear at all, so there's some kind of fuzzer.
They were related to JT.
Sorry? No, for JT you fix theta.
Yeah.
And here we don't know what is theta a priori.
But the way there's a flow which goes to the zero component of that.
Sorry?
There's a flow which goes to the zero at most.
It's a different story. Different story. When you want to flow in JT, you already fix theta. And for example, if my object is semi-stable but not polystable, then it's kind of essentially equivalent to JT flow in this case, and then you get this complicated behavior. But here we don't appear know what theta. We've got several thetas, and this kind of chooses by itself. Yeah, so that's a geometry of stability in case of representation of quiver, and there are kind of two analogs.
definition of stability, is the consequence that there are no harms from like semi-simple object of theta to degree theta to a semi-simple object of
It now, from properties of stability follows this Holmes goes only in one direction. Kind of for torsion, you cannot have maximum torsion, which is big theta, to non-torsion, which is small theta. Actually, I think I forgot it. It should be part of that. There's no Holmes.
And some other things as well.
That's it, actually.
Shift by one.
Yeah, there's some details. Yeah. So this is kind of clear example, but it's very boring. Yeah, we already know what is T structure. Stability gives a kind of exotic T structures, not which we don't know a priori.
Before I go to executive, consider bundles and curves like the
No, in general, for general categories, yeah. Yeah, so the kind of ultimate goal will be Foucault category of X omega, and this Foucault category of symplectic manifold, and for Z grading I need realization first Chantas, and for stability I need more, I need kind of volume, complex volume form. It will be X will be 2n-dimensional manifold, it will be n form, let's say closed and maybe primitive. X is complex coefficients, and such that it's positive, not any restricted to any Lagrangian subspace is non-zero. Yeah, so it's like holomorphic volume form on Calabi-Yau, is scalar structure, arbitrary Taylor form. Yeah, so you get such things, and the semi-stable object, as I explained in the first lecture, should be objects supported on special singular Lagrangian subsets. And with theta special means that argument of omega of O restricted to tangent space is theta, and ambiguity by multiple of pi is exactly related to choice of shift of complex. Inside, yeah, so this is a special object, and what will be the flaw? So the question is why we should believe that it's a stability, because why any object should be decomposed to semi-stable by some kind of flaw, and flaw here is given by different formula. If you get, let's consider kind of smooth part of my singular Lagrangian guy. The derivative with respect to time should be given to argument of the restriction of, actually not argument, I just say, the graph of differential of function, which is argument of restriction of complex volume form to my non-special Lagrangian. So this will be roughly like mean curvature flow. It's something which kind of make the total length smaller. And here, by the way, you consider the absolute value of this guy, these things also decay, some kind of mass decays. So we cannot run to more complicated things, to less complicated. And here's the length decays. And that's a rough idea why one should have certain, this things should split your Lagrangian to some semi-stable pieces. Okay. Yeah, that was kind of informal introduction to more formal part. Now, I will return to this example later. Now maybe I'll write something, now go back to the case of curves. There's something simpler than that. Yeah, here it's complicated ODE, and there is a simpler ODE. Suppose I have a viewer over non-Archimedean field. And I mean something like Laurent power series in some variable capital T. Then I have notion of so I can have either discrete variation, or I can have real variation like Noether field. Discrete variation could be also periodic numbers, like this. Okay, so I have a viewer of non-archimedean field, and let's again think about representation degree 0. So I get notion of norms, but now consider collection of norms. Such that each arrow of my viewer will preserve unit ball. And norm is back to arrow goes from vector to 2, and operator norm is less than 1, so it doesn't increase the norm. So I consider only such norms, and again, I think I have my complex numbers in the upper half plane. What I can call polystable object, yeah, definitely the same theory. It doesn't matter which field you use, you have notion of polystable objects. But what kind of notion of harmonic metric? Analog of this equation. Analog of polystable metric. Polystable object plus harmonic metric. Metric will be the following. It's such norm, collection of norms, such that if you have norms, then then you can make. It's better to think of for Noether field. Then you can make reduction to the residue field. The residue field is theta semistable. Yeah, so let's declare this to be harmonic matrix, and I'll go harmonic matrix. Yeah, it's easy to check that if you have such things that it's special fiber theta semistable, then the subject will be theta semistable in over the whole field.
But the big thing is polystable.
Yeah, in over non-archimedean field, there's really no difference between polystable and semistable. Those iterated logs, it's all the complicated story completely disappears. And what will be the flaw?
By reduction to residue field, you mean you take the
6
vectors of norm 1
and divide by norms less than 1, yeah. And here there's a very stupid flaw, kind of really stupid flaw, namely in the following way. So we should write some kind of equation like this. So now think about the following. You have vector space of a non-Archimedean field, and you want to change a little bit the norm. What is the speed of this change? You claim that the speed of the change can be thought as R filtration on reduction to the residue field. Yeah. What I mean by this reduction to R filtration, it's you see that if you have vector space, and let's speak about individual vector space. You get vector space and you get certain filtration. vector space over, let's say, residue field times special vector space, special fiber. Now you choose a basis compatible with filtration. Choose a basis compatible with filtration. And consider kind of same family of norms in diagonal basis. If you change basis, then for small t you apply some kind of upper triangle part with strictly negative things. It means that for small t you get the same stuff. So for each tangent vector you get canonical germ of a path in this in this story. And moreover, for any path you can make also some canonical path. And then one can analyze and see that this flow really exists. It makes sense. And the R filtration. Yeah, the R filtration which you use as a speed will be harder or similar filtration on the things of the residue field. Yeah. So that's a differential equation. ODE for flow will be that speed is equal to harder or similar filtration. Okay. And then the claim that serves will be fine. And this is actually a theorem, I suppose. I introduced to some very, very general nonsense. Extremely general, namely, so we have clears, but maybe with relations. So after you deform it, we will be few representations. So it's kind of not flat deformation of clear at all. But how one can analyze this situation categorically? Kind of consider kind of formal one parameter deformation of a category. Yeah, and principle, if you have, there are kind of two answers. One can say that you get, if you want to keep some kind of base field, you consider formal path in Maurer-Cartan space for Hochschild cohomology of your category. One can formulate things that's kind of even more softer terms which are applicable to mixed characteristic case and so on. Namely, one should do the following. So let's think geometrically. Let's think our category like, I don't know, perfect complexes of some gadget.
Actually, will you want to know homology or complexes?
Complexes. Yeah. So think geometrically. Suppose you get some vibration of a disk, and you get special fiber. And you get total space, and you get generic fiber. So you get. So what I get category CS. It will be category should deform. It will be like perfect complexes on special fiber. It will be some stable triangulated category. Then we get some another category C0, which will be things in the formal neighborhood. Now, for the clear, you can think it's representations of a residue field, representations of a ring of integers, or over Taylor series, and then we get generic fiber. It's unpunctured normal neighborhoods, things in punctured fiber.
And these three categories, I should view them as being defined over different fields, like different.
Even no fields.
Yeah, different rings.
No rings. It will be enriched by spectra.
Okay.
Very, very general story, yeah.
But different ones.
No, just it's abstract tranquility category which is in homotropy sense, enriched by spectra. No other constraint. And this factor which can restrict its kind of inclusion of special fiber total space. This will be things that can called G low star direct image.
But let me ask again. So C0 does not remember you do not remember the map to the disk.
Yeah, it's just fiber. It's representation set of quiver of the residue field. Yeah.
No, I'm asking C0.
C0 is kind of perfect complexes supported on special fiber, which are pretty bad category.
Yeah, but I'm asking, do you remember the structure of the fact that it sits over this formal disk, or do you forget that structure?
Yeah, no, I will just say the whole story about formal disk, how categorically to encode it.
Okay.
Yeah.
Why did J lower star go in that direction?
For J upper star. Yeah, sorry. J upper star. You're right. We get J upper star. And yeah, if you think in geometric expression, this functor has a adjoint. Yeah, that you get what is it? J low star and 0 to C0 and get J upper star. Get adjoint functors. And then. Yeah, in fact, if you don't know whether this neighborhood is formal or not formal, you can still get adjoint functors. And then you can get from C0 maps to you get adjoint functors, and in particular you get comonad T in CS given by composition. First you take derivation, then go back. The comonad is rule to notion of monad, so you get mapped from T to identity functor of CS and get mapped to T square and higher coherences. So you get a natural comonad. Actually, what I will describe in case of disk with discrete valuation, not continuous valuation. Yeah, so get this comonad, and what I will want for this comonad, first of all, this category C0 maps to category of T comodules. It's in any an arbitrary station is two adjoint functors. Object on a big guy gives it these comodules, and these T comodules can be sorted actually object on a formal completion. So we ask it to be equivalence. So C0 is completely constructed as defined as algebra of T comodules. Yeah, that's actually station responsible for arbitrary algebraic geometry, closed subset in a smooth variety. You have shift supported on a closed sub scheme, you get pull backward forward, and formal neighborhoods will be these T comodules. But now I want to say that it's things of kind of codimension 1, and moreover, it's a disk, and I didn't even want to ask that this is a projection to disk. I want to say that normal bundle is trivial. And kind of normal bundle is trivial. I say that it's cone of this coadjunction T to identity CS is isomorphic to identity CS shifted by 2. Yeah, again, if you consider situation of, let's say, product hypersurface some variety, it will be tensed by line normal bundle and shifted by 2. And now take normal bundle is trivial, so I don't even ask a projection, so it's very first order deformation. Yeah, so I get such situation. Then one can define C generic is defined as a quotient of C0 by image of G log star of CS, kind of torsion shifts, and that will be my category of generic fiber. It's another term, but category is no fields entering into the game. No? Good. Now this is theorem. Assume this category of special fibers carries stability condition. Z, you have central charge, and suppose it also has a support property in the sense which I explained. Very rough one, so discreteness of this special values of central charge. Then there are two things. Yeah, so one thing is the following. We get this diagram. In the diagram, let's consider K0 of C0 matched to K0 of CS matched to K0 of C generic. Yeah. This map is epimorphic by definition because any object in C generic is represented by some object in C0. The claim that there exists a kind of canonical, actually unique map here. So get map from C0G to C0S, and then one can map by central charge to C, so you can have central charge on generic fiber, and then we define things like in absolute expression, like we're doing in concrete expression, define what are harmonic metrics are choices of representatives which are restricted to special fibers are semi-stable. Define harmonic representatives as those whose image in CS is theta semi-stable. Then it will be stability condition on C generic. Now that's the theorem. I didn't say anything about flaws. One can introduce some flaws. It's not necessary, but it's possible.
In this context, is there some difference between the words harmonic and stable?
No, stable is object. Harmonic is kind of chase of norm, metric. In chase of metric, it's kind of chase of lift to this special fiber.
So what does it mean that it is a stability condition?
It is stability. No, consider. No, the stability condition is object which have harmonic metrics form a stability. Flaws one should define on some case space of metrics and metrizations. And one needs some kind of continuous parameters because here discrete relation. What is metrization? For object E kind of generic and C generic, E is a choice, by definition, it's a choice of model E0 in C0 such that E0 maps to EG by localization, and choice of filtration by numbers from 0 to 1, kind of parabolic structure on G log upper star of E0 and 6. And filtration, I mean, finite choice of numbers and map from Dinkin quiver to my category. Yeah, so it's correspond to parabolic structure in usual context for bundles. Yeah, but I will not use flaws directly. So how one can prove this theorem? The idea is just not to use continuous time, but discrete kind of. We want to, if I have my object, I choose some model, that's our object in C0, and I want to check, kind of, again, improve it in maybe infinitely many steps and get, see that I can eventually use actual hardness filtration. So the story is the following. I have given object, given object in generic. I consider a model E0 and C0, and now I want to kind of modify it step by step. If I have a model, I get things of special fiber, and it has harmonious infiltration. And in particular, it contains kind of this lowest part, lowest non-zero part. I should call it F, which was some E greater than equal to theta. F special. So it's a kind of part of this my story. And again, what one should think, it's even, let's forget about this picture. Think about this vector bundle on a formal puncture disk. I get vector bundle non-puncture disk. And here I get subspace in a fiber at 0. Yeah, that's the story. Yeah, so we get bundle of puncture disk and subspace at fiber at 0. Consider new bundle whose sections are sections which at 0 lie land in your subspace. And this can be set categorically. So you get kind of a new guy. How we can do it? Because we get this inclusion, we can kind of translate category, go to some exact triangle, and by adjunction we get map from E0 to direct image, and we consider kernel of this guy. And this will be kind of E0 prime. We get a new model. Again, it's after localization gives the same E generic. It's a new model. And now consider values at special fiber. Something funny will go on. The guy which was subspace became a quotient space. So the things are exchanged. Exchange the role. S. And what was a quotient became a subspace because of this exactly this trivialization of normal bundle. Otherwise, you can multiply by normal bundle. So that things are exchanged their role. And now, what goes on? You have a new model, and something which will be something simpler after this process, because it was a hardness infiltration, and in general, one can speak about a mass of the object in translate category, the stability, and some our absolute values of this central charges of constituents. In geometric situation, it will be volume of kind of low bound of the volume of kind of the Lagrangian representatives of this story. So you get a mass, and the mass of this guy will be mass of this guy plus mass of this guy because harmonic infiltration. But now we exchange their role, and then the mass will be of harmonic infiltration will be only smaller. It's kind of satisfies random inequality. So the mass of special fiber of restriction to is less than mass of G of E0. So the mass are started to decrease. And you repeat procedure infinitely many times because it's, they start to decrease and we have discreteness of the values, they stabilize at some point. So
Is this discreteness of values, is it ever true in the geometric situation?
Yes, yes, because it's you have special Lagrangians, it's image of this lattice of middle homology, but also we can bound degree of class and homology by total mass, and you get finite, yeah, it's kind of geometric arguments for compact varieties, yeah, one can argue that it's, for bounded geometry, I think it's automatically follows. You have bounded geometry.
But for example, suppose you wanted to use your theorem to prove that existence of stability conditions of high dimensional varieties.
Yes, yes.
You degenerate them with some sort of union of torque or something.
No, I don't do anything. I just have symplectic manifold and automatically this central charge slice is a countable subset, but if you have bound value of central charge, then the classic homology is uniformly bounded to get only finitely many possible choices. Yeah, so we get the simplification, and at some point it kind of stabilizes. So if we do next step, we apply again Farrow's filtration, we do the same. And what does it mean, the stabilizers? It means that this mass of this guy is equal to mass of this guy plus this guy. It means that this sequence splits, and it splits canonically. By vanishing Holmes. Yeah, so we get canonical splitting of this filtration. And then now fs became sub-object, and then you method between quotient object is equal to direct sum, and you repeat infinitely many times. And what happens? It's kind of pure categorical game. Now we forget about stability. We get this modification of objects, adjoint functors, and suppose on each step my exact sequence splits, and I apply again and again splits. Then if you go to infinitely many steps, it will be exactly object comodule over comonad, which you construct a subbundle. Yeah, so it's literally this infinitely many time repetition. It's a kind of definition of what is a subbundle. Yeah, so that's, and then you repeat for next term Hartwig reflection, and then you are done. Yeah, so that's basic kind of categorical discrete time argument, which shows that things are completely fine. And so the story of this example is the following. When with Ludmila, Fabian, and Branov we start to think about this, we thought it should be kind of first trivial example, no trouble. But then a few weeks ago or months ago, kind of Branov thought, but why on the earth this map should exist? And it's very easy to construct examples of categories, some formal deformation, when you get two objects which have different class and K-Surian, and under deforming they have become isomorphic. So you have different lifts. This map cannot exist. But then one can turn this argument around. This thing works, and the corollary is the following. If such maps doesn't exist, then category special fiber doesn't have stability condition. Yeah, so it's kind of save our day, just turn problem to a solution. Okay. Yeah, so it's truly some kind of most basic example how the stability works, and with flows or with discrete time, continuous time. And now I'll go to some hypothetical example of the following nature. It's actually a return in disguise to Foucault category, but not talking about Foucault category. Suppose X is algebraic variety, and Calabi variety, say, of a non-Archimedean field. Then I get analytic space, the required spectrum, and suppose I get a projection this guy's to some base, it will be non-Archimedean SYZ fibration. Yeah, so it's I didn't give you a definition what is non-Archimedean SYZ fibration, but kind of the basic example, it's already very non-trivial with the following. X will be abelian variety of, let's say, n-dimensional abelian variety, and X analytic to, and B will be a real torus, usual kind of generalization of Tate curve. Yeah, so this is a horrible thing. You get torus, and I claim that, yeah, then on B one can make a completely formal construction. Just in this case, because B will have natural integer affine structure on tangent space. I consider cotangent bundle of B divided by integer cotangent bundle of B, total space. You get some 2n-dimensional torus, which will carry a completely flat symplectic structure. It's let's symplectic structure. It's a real object, and kind of SYZ mirror symmetry says that Foucault category of this guy is equal to coherent shifts of this guy. But and now what my philosophy for stability says should be what are stable objects. We should choose a volume element, not complex volume element, complex volume form. Choose complex value form, non-vanishing on Lagrange subspace. Maybe this non-constant coefficient, so it will be infinite dimensional space of choices. It modifies Monge-Ampere equation of special Lagrangians, and I can try to in Foucault category speak about this object with singular support, with support on some singular sets and which are special Lagrangians, and then there will be what object Foucault categories, and there will be the solution of bounding a chain. Yeah, it's all horror, but my claim is that one can kind of make a formulate these things without using directly Foucault categories. So the idea is that objects of Foucault category X dual represented as constructible shifts on singular Lagrangian subsets plus bounding a chain. All this core can be reformulated in much simpler terms as an object of perfect complex of X analytic with norms. And norms, one considers reduction to norms. You get again Novikov ring and consider ring of integers. So formulated. Algebraically.
Here you, so to speak, assume homological layer symmetry.
Yeah, assuming homological symmetry. Yeah, but here in this reformulation, you see this complicated gadget will be replaced by something algebraic. Yeah, I don't have still good details, but what are basic example of object of the norm? And take some open domain in view, open domain.
So why objects with norms?
Yeah. So the idea is this Lagrange manifold represent how norm behaves. It's the same story. Yeah, that's kind of
Every Lagrange norm.
everything. Yeah, no, this will be just the same story. Let me give you example. Consider open B, and you can maybe, because we can embed an array, and use local coordinates and consider trivial line bundle. Trivialized line bundle on U. And to the norm, you get norm of section 1 at point x and x will be certain function phi of x, exponent of phi of x, of phi of projection of x. If phi is just some function from U to R, some C infinity functions. If you have any C infinity functions, that gives you a norm on trivial line bundle. And my Lagrangian subspace subset is submanifold actually here will be graph of differential of this function phi modulo integer part of cotangent bundle. So project is cotangent bundle. Yeah, that's a picture. And
so this idea is that you're proposing some sort of a lift of homological mirror symmetry is something compatible with this metric. That's the,
Yes. Yeah, this actual geometric object will be metrics. Yeah. So Lagrange manifold will be df, and now one. So the proposal is the following: if you have object with norm, I will associate a subset, maybe with some Lagrange subset with multiplicity. And how I associate the subset? Yeah, so it's kind of proposal is the following: if you have object with norm on X analytic, then I will construct in some way Lagrangian or chain, maybe closed singular chain with Lagrangian support. In this X2. And what could be the formula for this chain, at least for support? So the suggestion is the following. Yeah, first you see this is Lagrange guy, it's not exactly a cotangent bundle. We can make lift to cotangent bundle. So this future Lagrangian guy sits in cotangent bundle divided by integer part and have a lift. Let's go to one dimension. So if you have something in cylinder, some kind of curve, then we get this curve, and this curve get integer get n kind of nx divided by integer slopes, guys. So we get infinitely many branches. But it's Lagrangian guy, but it's not conical. And one can make it conical adding one variable. And then the idea is the following. Let's consider on B cross R. R with some stupid, let's call it tau. We consider sheaf. Sheaf maybe. Let's think about bundles, because I think it works to triangulated cases as well. You consider set of sections of U on -1 of some point, small domain. So the norm of S is less than tau everywhere. Because if you have a norm, you can kind of rotation, get natural shift, and now consider singular support in terms of Kashivara and Shapira. And simple calculation goes as single support will be conification of this guy, and then we mod out, and we get things. Yeah, so the proposal is to give really definition of one class of norms then the whole thing applies, and then a bit single chain which represent the first the class in middle homology which correspond to chain class of your bundle, and then I don't know what to do else, flow or not flow, but we lead again with the same hard analysis special Lagrangian, singular special Lagrangian guys in real terms anyhow. Yeah, so it's unavoidable in a sense to have this special Lagrangian, but that will be really clean definition, at least proposal for definition in realm of algebraic geometry. So people, and suppose you have in departments that kind of two groups, algebraic geometers and analysts, and they started to talk to each other. Okay. Okay. Thank you.
So are there any questions?
How does this relate to these, Collins and Yao vectors?
Sorry?
Collins, Tristan Collins and Yao vectors along this proposal of
They have over complex numbers.
still, you can include it.
Yeah, no. The trouble is the following. They have proposal for it doesn't really work what they do it because they don't consider complexes. They consider normal things. And actually, from this picture, this is a really funny thing which you can expect, because in this SYZ picture, you get vibration of torus some base. This Lagrangian manifold can have folds. So it means it is described as a complex of different lengths and different pieces of your manifold. So it looks like it should be composed by real domain, always open kind of codimension one boundaries, and described as complexes of different lengths. It will be kind of homotopy through the boundary. And it says that it means it's also the same should be true on complex numbers. So it should, if you want to eventually describe geometrically stable, some kind of non-trivial stability condition should.
But there should be some kind of intersection when you look at the bundle.
Yeah, as you can see, only line bundles and so on, but it's definitely deficient proposal as it is. It's not complete.
My question is whether this objects of curve X and with norms and sets of objects from categories and things like that.
Yeah, they should form tranquil category. Yeah, sure.
That would be like the equivalent to something kind of
for category of ring of integers
Right.
before localization, before making returning that. Yeah, exactly.
Other questions?
Yeah, I think we.
So I wanted to ask about now a different application of your theory.
Yeah.
So suppose I want to make a stability condition on, let's say, Calabi-Yau threefold.
Yeah.
You might imagine you take your Calabi-Yau, which will stay in the blood algebraic geometry,
Yeah.
degenerate it to union of toric varieties,
Yeah.
make stability condition on union of toric varieties,
Yeah.
and now you're given a procedure for deforming.
Yeah, but you get different. Then you get different category. You change coefficients of your Calabi-Yau.
Yeah, I mean, it's Calabi-Yau where it's non-archimedean.
Yes, yeah. Now, but if you consider Calabi-Yau of non-archimedean field just with one variable, it's I think it should be equivalent to this usual, the things which I described for individual symplectic manifold.
Yeah, sure, yeah.
Yeah.
But I mean, can one conclude from your theorem the existence of Bridgeland stability condition on this?
Which theorem? No, those theorems only for stupid example. Yeah.
The theorem you stated had some sort of, what was the restriction to some stupid example?
No, it doesn't really go, yeah. No.
Yeah, so why is that?
Yeah, I don't know. No, I got feeling it's.
I'm asking that
It's those two cheap theorems.
Yeah, but which hypothesis of that theorem excludes this kind of application?
Yes, no, so it will mean that it's what we call harmonic metric, very, very degenerate gadget. Maybe this category we will see in the special fiber doesn't have stability condition. I don't know.
That might be a slightly similar question, which is, suppose you have something with a special Lagrangian skeleton.
Yeah.
Can you then try to apply the...
No, special Lagrangian skeleton gives us only some small part of these stable objects here, because For other, no, of course, no, in principle, one can use one Lagrangian skeleton for describe the whole category, as I explained, just remove this Johnson divisor, but it's not good for purposes of stability, because it's you describe this category up to after inverting a small parameter, and here we don't want to do it.
Any further questions? Okay, so let's thank you.